Hello, today we're going to talk about resonance and formal charge. So formal charge is a way that we can kind of decide between which of a couple possible structures are more stable. So the structure with the least number of formal charges tends to be the most stable. So if you have a lot of zero formal charges, that's good. And if you have more numbers or different numbers, they tend to be less stable structures. Also, you want to have structures with the more negative charge on the more electronegative atom. Because if it's more electronegative, it's going to attract more electrons, giving it that more negative formal charge. So the steps for finding formal charge, the first thing you want to do is determine the normal number, the usual number of valence electrons for an atom. And then you're going to subtract the number of electrons that are assigned to the atom in the structure. So each lone pair electron will count as 1. And then each bond counts as 1. So let's say, for example, you have an oxygen atom as 2 lone pairs and 2 bonds. A number of electrons assigned to it would be 6. So you would count 1, 2, 3, 4, 5, 6. 6 electrons assigned to it. Since oxygen normally has a formal charge of 6, you would do 6 minus 6, so its formal charge is 0. And then if you add up all of the formal charges on all of the atoms in the compound, it should equal the charge on that compound. So if it's a normal molecule, it'll have a charge of 0, and the formal charges should add up to 0. If it's a polyatomic ion, you want the formal charges to add up to the charge on that ion. Okay, so let's look at HCN. Each has 1 valence electron normally, carbon has 4, and nitrogen has 5. So that means altogether we have 10 valence electrons. Carbon is the least electronegative, it goes in the center. So we have hydrogen and nitrogen attached to it, so that would be using up 4 electrons, and I have 6 left. So hydrogen already has a full, quote, octet, but hydrogen doesn't, because it only has the 1s orbital, it only needs 2. Nitrogen, on the other hand, should have the full octet. Right now it only has 2 electrons. It needs 1, 2, 3, 4, 5, 6 to fill up its valence shell. So that uses up the last 6 of our valence electrons. So this is a possible Lewis structure. But it's not quite done, because so hydrogen's octet's good, nitrogen's octet's good, but carbon does not have a full octet. Right now it's only sharing 4 electrons, 2 for each bond. Carbon wants a full octet. So what we would do is then we change lone pairs into double bonds, like that. So now carbon has 6 electrons. And then last but not least, we want to change one more. So there we go. We would get the carbon now has 8, so it has a full octet, and nitrogen also has 8, so it has a full octet. Let's go ahead and check the formal charges here. Carbon, well, let's start with hydrogen. Hydrogen normally has 1 valence electron, and right now it has just 1 bond. 1 bond. So that means there's 1 electron assigned to it, and when we subtract, we get a formal charge of 0. So that's for hydrogen. Now for carbon, carbon normally has 4 valence electrons, and right now it has 1, 2, 3, 4. 4 electrons assigned to it. So when you subtract, you get the 4, or you get the 0 formal charge, which is good. Zeros are great. Our last one is nitrogen. So let's do orange. Nitrogen normally has 5 valence electrons, and right now it has 1, 2, 3, 4, 5. 5 electrons assigned to it. So its formal charge is also 0. That means since all of the formal charges are 0, it's very stable. You have the electrons placed correctly around the atom, or around the molecule. Let's say, for example, you were doing this and maybe you got your octet rule wrong, but you got that there were that the bonds were distributed like this instead. Well, in this hypothetical situation, hydrogen would have, it normally has 1, but right now it has 2 assigned to it. So it has a formal charge of -1. This carbon normally has 4. It has 4 assigned to it, so its formal charge is 0. That's good. But this nitrogen normally has 5, and right now it has 4 assigned to it. So when you subtract, that gives you a formal charge of +1. Now, all of the formal charges do add up to 0, but because having formal charges is less stable than not having formal charges, we know that this structure is not a good example. Now in the last slide we were looking at HCN, and we changed some of those lone pairs into double bonds to fill up carbon's octet. But there was only really one place for us to do that because hydrogen can only have 2 electrons because of its s orbital. But if there's more than one possible location for you to make a double bond, you need to do all of the possible locations. And then you'll draw 2 or 3 or 4 or 5 or however many structures you need to show all of the different possible locations for the double bond. And then you draw these double-headed arrows in between them. All right. So in this situation, it says acetate. Okay. Whenever you're drawing an ion, you want to put these brackets around the ion. So acetate is HCOO minus. That's the acetate ion. Carbon has the least electronegativity. And you'll put the other atoms around the outside. There are 17 valence electrons for those atoms, plus 1 for the ion charge. So there's 18 total electrons there. And I just used 6 in the bonds. So that leaves us with 12 valence electrons to fill in the octets. Hydrogen's already set, but oxygen needs to have a full octet. So there we go. That uses up all 12. I don't have any left for carbon. So, because carbon also needs that full octet, you need to change one of the lone pairs into a double bond. But there's 2 options, right? I could choose a lone pair on this oxygen, or I could choose a lone pair on this oxygen. And if I chose to change one of these lone pairs to a double bond, you'd wind up with this structure. But if I chose to change one of these lone pairs to a double bond, I would wind up with this structure. So because there's 2 possibilities, you have to draw both of them and put a double-headed arrow in between. Now the reality is it's going to wind up somewhere in between those 2 structures. The electrons are what we call delocalized, so they're able and free to move around the structure. So that's what this image here is showing, that the 2 electrons that are turning into the double bond are actually moving in between both locations. So that's what this means here. It looks like a dashed line, so each one kind of has like a 1.5 bond, 1.5, 1.5, but we don't draw it that way, and you'll never draw it that way. You always have to show the 2 possible locations. But this is like what it's doing. This is another example. This is ozone, and so these are the 2 possible structures for ozone. In reality, each one of those bonds is like a 1.5 bond. Now here's just another common example. This is benzene. Benzene has a ring with alternating double bonds. So it has 2 resonance structures because you could have the bonds alternating this side or this side. So it winds up really stable, and what happens with those electrons, because there's 6 electrons that are delocalized, is that they wind up traveling all of the way around the ring. Okay, so you have 6 electrons free to travel around on all of those different locations in the hexagon. I didn't draw the atoms for my representation, but it makes benzene super stable because it has those 6 delocalized electrons. Okay, so for this one, let's go ahead and count our valence electrons. Carbon has 4. There are 3 oxygens with 6 each, so that's 18, and the -2 charge means we add an extra 2. So I have 24 valence electrons to work with. Let's go ahead and put carbon in the center, and I have my 3 oxygens around the outside. I just made 3 bonds with 2 electrons each, so that used up 6 of my electrons. And then I need to fill in the octets of the outermost atoms, so each oxygen already has 2 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So that used up all of those valence electrons. However, that carbon only has 6 electrons assigned to it, basically. It really needs a full octet, especially because it's in the second period. So what I need to do is I need to take one of those lone pairs and change it into a double bond so that oxygen still has a full octet and carbon now has a full octet. Okay, so this is one possible structure with my -2 charge for the carbonate ion. But why did I pick this top oxygen? Well, I just picked one. So you have to draw an additional structure showing where you picked a different oxygen atom. And the oxygen with the double bond should only have 2 lone pairs because we want to make sure our octets are still satisfied, like that. But wait, there's one more, because there's one more possible location where you could have put the double bond. And make sure that you fill in the octets appropriately. The one with the double bond should only have 2 lone pairs. We're running out of space. So those are your 3 resonance structures for carbonate. And remember that the actual carbonate molecule will kind of be an average of the 3 because those electrons that are in that pi bond are delocalized. They're free to move around the whole molecule, lending it extra stability.